Hello everyone, and welcome back to the channel, the CyberForgeAI, your practical lab for secure code, ethical hacking, and future-ready projects. Today, we're going to tackle a famous and fascinating puzzle, the Tower of Hanoi. If you've ever felt overwhelmed by complex coding or math problems, don't worry. Today, we're going to break this down visually, so it's super easy to understand. Let's get started. Take a look at the screen. You'll see 3 pegs, the source peg on the left, a helper peg in the middle, and a destination peg on the right. The goal of this puzzle is simple. We need to move an entire stack of disks from the source peg to the destination peg. But to do this, we must follow 2 very strict rules. Rule number 1. You can only move 1 disk at a time. Rule number 2. A larger disk can never be placed on top of a smaller disk. That's it. Those are all the rules. Let's see how this works in action, starting with the absolute simplest case. Here we have just 1 disk. Since there are no other disks in our way, we simply pick up disk 1 from the source and drop it straight onto the destination peg. Easy, right? 1 disk takes exactly 1 move. Problem solved. Now let's step it up a bit. What happens when we have 2 disks? Remember our rules. Move 1 at a time, and no big disks on small ones. To get our bottom disk, disk 2, to the destination, we first have to get disk 1 out of the way. So, we move the small disk 1 to our helper peg. Now the source peg is clear, so we move the large disk 2 directly to the destination. Finally, we move disk 1 from the helper peg to rest on top of disk 2. We did it. 3 moves total. Let's look at 3 disks. This is where the magic of the helper peg really shines. Our ultimate goal is to get the largest disk at the bottom, disk 3, over to the right. But to do that, we have to move the entire stack of 2 disks above it onto the helper peg first. Watch closely. Disk 1 goes to destination. Disk 2 goes to helper. We put disk 1 on top of disk 2. Look at that. Disk 3 is now free. We move disk 3 to the destination peg. Now, we simply move disk 1 out of the way, disk 2 to destination, and disk 1 finishes it off. 7 moves. Are you starting to see the pattern? Here is level 4. No matter how tall the tower gets, the logic is exactly the same. To free up the bottom disk, disk 4, we first need to move the top 3 disks to the helper peg. Disk 1 goes to the helper, disk 2 to the destination, and disk 1 on top of 2. Now, disk 3 to the helper peg. We shift disks 1 and 2 over to join it. Our top 3 disks are perfectly stacked and out of the way. Disk 4 goes to the destination peg. Now for the final stretch, moving that stack of 3 from the helper peg to the destination. We shift the smaller disks temporarily to the source peg, slide disk 3 into place, and finally bring disks 2 and 1 home. 15 moves exactly. Now, let's see this. A tower of 5 disks. At first glance, this looks incredibly complicated. But remember our golden rule. To move the biggest disk at the bottom, we just need to move the stack of 4 disks sitting on top of it over to the helper peg. Watch the algorithm do its beautiful dance. Notice how the smallest disk, disk 1, is constantly bouncing back and forth. It acts like a key, constantly unlocking space, so the medium-sized disks can shift around without violating our no big on small rule. Right now, we are just executing the 15 moves required to build our tower of 4 on the helper peg. Watch the algorithm work. We are simply repeating the 15-move sequence we just learned for 4 disks. Notice how the smallest disk constantly shifts back and forth to unlock space for the larger ones. There's our stack of 4 safely out of the way. Now, disk 5 is free to make its move to the destination. To finish, we just bring that stack of 4 over from the helper peg to the destination peg. We follow the exact same rules step by step until the entire tower is rebuilt on the right side of the screen. Now just 3 disks remain, and by using helper peg, we'll move the disk 1, 2, and 3 to the destination. 31 moves total. By breaking a massive problem into smaller, repeating steps, even the Tower of Hanoi becomes simple. Here is a simple code for Tower of Hanoi in Java. For n number of given disks. Here's our Tower of Hanoi method. Every recursive function needs a stopping point. Our base case is simple. If n equals 1, meaning only one disk is left, we just print the move from the source peg to the destination peg and stop. But if we have more than one disk, we follow the exact visual steps we just learned. First, we move the top stack out of the way. We call our function again for n1 disks, but notice how we swap the pegs. We are using the helper peg as the temporary destination. With those smaller disks safely out of the way, the source peg is clear. Now, we print the command to move our largest disk directly to its final destination. Finally, we bring the smaller stack home. We call the function one last time to move those n1 disks from the helper peg onto the destination peg. In our main method, we just get the number of disks from a user, call our function for pegs A, B, and C, and the algorithm handles the rest. It's that simple. And that wraps up our deep dive into the Tower of Hanoi. Thanks for watching. Like, share, and subscribe if you like the video.